In this video, we will look at two more very typical optimization problems. But before diving into the problems, let me remind you of the overall procedure. We read the question, fully understand it so that we can draw a picture and assign variables. Once we have done so, we want to think about what quantity, call it Q, that we would like to maximize or minimize, and we write a function for it. Now the problem is that this function will typically involve more than one variable. So what we do is we use conditions given in the problem to somehow express it in terms of one variable, and then use the calculus methods that we've built up in this chapter to determine what the maximum or minimum value will be. So let's find the point on the parabola y squared equals 2x that is closest to the point 1, 4. Okay, let's draw a picture of the situation. So we have the parabola y squared equals 2x, so think x equals 1/2 y squared. That's going to be a parabola opening in the positive x direction. So roughly speaking, something that looks like this. And what we would like to do is determine what is the point on the parabola closest to the point 1, 4. And what we need to do is set up a function that's going to give us the distance between 1, 4 and a point on the parabola. That would be the thing that we want to minimize. So what we need to think about is if we pick another point on the parabola, say x, y, what is its distance, I will call it big D, away from that point 1, 4. So big D is going to be the distance between 1, 4 and the point x, y, which is on our parabola. And by the distance formula, this distance is going to be the square root of the difference of the y values squared plus the difference of the x values squared. And going back to our guidelines, we've drawn a picture, introduced some variables, x and y in this case, and we've written down the quantity it is that we would like to minimize. What we need to do is use the information given to somehow express this in terms of just a single variable. That is x in terms of y or y in terms of x. But the equation of the parabola is what does that so nicely for us. Y squared equals 2x. Well, this is equivalent to saying that x is 1/2 y squared. So we can take the single x that we see in our equation for D and replace that with 1/2 y squared. So D, solely as a function of the variable y, is going to be the square root of the quantity y minus 4 squared plus 1/2 y squared is what replaces the x value minus 1 quantity squared. And this is the function that we need to maximize, or excuse me, need to minimize. And we say, what is the interval where y can be in? Well, here looking at, graphically, where can y be and still be a point on the parabola? Y can be anything. So y in this case is in the interval from -infinity to infinity. And here is where we are going to make a very important observation that simplifies the problem. So in this case, the function D is the square root of something. And the square root function, if you think about it graphically, is a nice increasing function. So wherever the function D is going to assume its minimum value, it's going to be when whatever under the square root is as small as possible. So the function D is minimized where D squared is minimized. So we don't actually have to deal with the entire square root. what we can do is minimize a simpler function. So what's underneath the square root. So we want to minimize, let's give it a new name now, let's call it f of y, which is y minus 4 squared plus 1/2 y squared minus 1 quantity squared. So a very important observation here, just to save us some time, it's more efficient. If you were to proceed and deal with the entire d function, if done correctly, you would come up to the exact same conclusion. So in order to minimize, we need to differentiate, but before doing so, I think it's worthwhile to expand everything out and then simplify as much as possible. So y minus 4 quantity squared is y squared minus 8y plus 16. And then we're adding on to this 1/2 y squared minus 1 quantity squared, which is going to be 1/4 y to the 4th. And then we're going to subtract away, in this case, y squared, and then we are going to add 1. So we have a positive y squared and a negative y squared term. So this ends up being 1/4 y to the 4th minus 8y plus 16 plus 1. And f prime of y, in this case, is going to be y cubed minus 8. So because we've made this simplifying observation, finding the derivative is now much more simpler and easier for us to work with. And what we would like to know is, where is this derivative equal to 0? Well, y cubed minus 8 equals 0 precisely then when y equals 2. So we have one single critical point. So what we would like to know is, does this critical point correspond to a maximum or minimum? And just because there's one critical point, we just can't assume that that's going to be the thing that answers our question. We always really need to go back and check and verify that this really is the case. So we need to think about the sign of f prime. So a test point to the left of 2 would be 0. 0 minus 8 is negative. A test point to the right of 2 would be 3. And see here, 3 cubed minus 8 is definitely positive. So in terms of our function, we are decreasing everywhere to the left of 2 and increasing everywhere to the right of 2. So typically we would say y equals 2 might correspond to a local minimum by the first derivative test, but here it's actually a global minimum, because decreasing everywhere to the left of 2, increasing everywhere to the right. So we have a global min corresponding to y equals 2. So if y is equal to 2, we go back to our original equation relating x and y, and we determine what our x value is. So the x value corresponding to this y value is going to be 1/2 times 2 squared, which is 2. And what we wanted to answer is, what is the point on the parabola closest to the point 1, 4? It is going to be the point whose coordinates are x equals 2 and y equals 2. So the point that we are looking for is 2, 2. So let's look at one more very typical optimization problem. Let's find the area of the largest rectangle that can be inscribed in a semicircle of radius r. So gosh, let's draw a picture here and see if we can represent this situation. So we have a semicircle of radius r. So that means, thinking half a circle. And let's see, if we give it radius r, this is going to be the top half of the circle, x squared plus y squared equals r squared. And because it's the top half, that's going to correspond to y being the positive square root of r squared minus x squared. And what we would like to know is that if we inscribe a rectangle, what would be the largest possible area that it could take on? So that is, if I put a rectangle in here, how big can we make its area? So the thing that we would wish to, in this case, maximize is the area of the rectangle. So we need to write down an equation of the area. And looking at this, I'm thinking that this coordinate of where, say, that upper right corner of the rectangle hits the semicircle, I'm thinking of its coordinates as being x comma y. So x represents, this distance coming from the origin to the right side of the rectangle. Y is its height. And with this observation, the function that we would like to maximize area would be base times height. The base is going to be 2x's times y. And labeling the x and the y in such a way is just going to make this problem work as efficiently as possible. And what we would like to do now is get this in terms of a single variable. And in order to get this in terms of a single variable, we note that y is equal to the square root of r squared minus x squared. So 2x times the square root of r squared minus x squared, where in this case, how big and small can x be? X can be as small as 0 or as big as r. And what we would like to do is find the maximum of this function. So we differentiate it, and in order to differentiate it, we're going to have to use the product rule. We're going to take the derivative of the first function, so the derivative of 2x is 2 times the second. And then what we are going to do is add on to this. I'm going to leave a little bit of space for some simplification in a moment. The first function times the derivative of the second. And when I differentiate the second function, we're going to need to use the chain rule. You take the derivative of the outside function, so 1 over 2 square roots, evaluate it at the inside function, and then multiply it by the derivative of the inside function. So we have a 2 over 2, which cancels. But in order to maybe work with this derivative as efficiently as possible, we want to combine into a single term. And that is get a common denominator. So I'm going to take the first portion, and I'm going to multiply it by 1 in a fancy way. Square root of r squared minus x squared over the square root of r squared minus x squared. So we get now a single fraction with denominator square root of r squared minus x squared. And in terms of what's in the top, well, we're going to have 2 multiplied by, well, the square root of r squared minus x squared times the square root of r minus x squared. The square root goes away. And then we are subtracting away what's in the top of the second term. So that would be minus 2x squared. And we need to determine where this is equal to 0. So a fraction will be equal to 0 when the top is equal to 0. So the top is going to be 2r squared minus 4x squared equals 0. And if we simplify this, that means 4x squared is equal to 2r squared. X squared equals r squared over 2, so x equals plus or minus the square root of that. So plus or minus r divided by the square root of 2. In terms of our problem, x is positive, so only one of those is in our interval of interest. So we're going from 0 to r, and we have the critical point, r over the square root 2. And we want to think, what is the sign of the a prime function doing at this critical point? So coming back to our simplified version of a prime, we see that the bottom is a square root and always positive. So it's just the numerator that's going to determine whether a prime is positive or negative. So if you were to plug in, say, x equals 0, you would get a positive number. So we are positive to the left of our critical point. If you were to plug in a number bigger than r over root 2, let's think maybe you plug in r, you would have 2r squared minus 4r squared. Well, that would certainly be negative. So if we think about what our function is looking like, it's increasing to the left of our critical point, decreasing to the right. So by the first derivative test, this x value is going to be a local maximum. But since it's always increasing to the left and always decreasing to the right, we can in fact say more, and we can say that we have a global max corresponding to x equals r over root 2. And now we need to go back and think, what question is it that we want to answer? We want to know what is the area of the largest rectangle that can be inscribed. Well, we can take this function that we have for the area and now simply plug in x. So the area of that largest rectangle is going to be a of r over root 2, which is 2r over root 2 square root of r squared minus, and then we have r over root 2 squared. So minus r squared over 2. And this simplifies down to being 2r over root 2. R squared minus r squared over 2 is r squared over 2, so r over root 2. So our final answer ends up being r squared, because the 2 cancels off with both the square roots of 2. In the bottom, they multiply together to give us 2. So the answer would be r squared, whatever our area units are, squared. So the maximum area we can have is r squared.